5.3a, graphs of the rational functions of the form f at x equals ax plus b over cx plus d. Okay, so this is going to be our focus for the next couple lessons. So rational functions in the form f at x equals b, so just a constant on the top, over cx plus d, so some expression like linear expression with a coefficient, an x value, and then plus a constant. Okay, what ends up happening is the vertical asymptote is going to be when we take cx plus d and we equate it to 0. Okay, so whatever that basically factor is in the denominator, when the denominator is 0, what's going to happen is we're going to have some number b over 0, and we cannot have that. That means it's undefined. Okay, so if we were to bring d over, we would have cx equals negative d, and then we divide both sides by c. That's where we get this from, x equals negative d over c. Okay, and if we have a constant in the numerator and an x in the denominator, and we're going to get there, we're going to have a horizontal asymptote of y equals 0. Okay, we saw that in 5.1. Okay, and rational functions in the form f at x equals ax plus b over cx plus d. So this is like a linear function over a linear function, if you guys see that. Okay, ax plus b, we have an x, we have a constant. It's kind of like mx plus b, right? So same's going to happen to the vertical asymptote. We're going to take the denominator. We're going to equate it to 0. Every single time, we're going to get the vertical asymptote of negative d over c. Now, if we have an x over an x value, okay, where the degree in the numerator, let's call it m, and the degree in the denominator are the same, what we have to do is we take the coefficients, like the leading coefficient in the numerator, over the leading coefficient in the denominator. In other words, our horizontal asymptote is a, I don't like that color, go deeper, a divided by c, which is right there. Okay, for the horizontal asymptote of y equals 0, formally, if we have x to the m over x to the n, like when we're looking at the exponent in the numerator and the denominator, remember b is a constant, so that means that we have the exponent like x to the 0. Okay, as long as n is greater than m, so the degree in the denominator is bigger than the degree in the numerator, what's going to happen is we are going to have a horizontal asymptote at y equals 0. Okay, it doesn't change. It's just y equals 0. Example 1. State the vertical and horizontal asymptotes of the following rational functions. So A, f at x equals 2 over x plus 3. So the horizontal asymptote is the easiest. Okay, we have a constant, which means we have x to the 0, and then we have an x to the 1. The exponent in the numerator is less than the exponent in the denominator. Therefore, we simply get y equals 0 to be our horizontal asymptote. Okay, our vertical asymptote, we take the denominator and we equate it to 0. We bring over the 3, we get x equals negative 3 is our vertical asymptote. Okay, B, f at x equals 5 over 2x minus 1. So again, we have x to the 0 over x to the 1. So our horizontal asymptote is simply y equals 0. Now our vertical asymptote, we take the denominator, 2x minus 1, and we equate it to 0. Bring the negative 1 over, it becomes positive 1. And then divide both sides by 2. So we have a vertical asymptote at x equals 1/2. Okay, C. Horizontal asymptote. We have an x to the 1 over an x to the 1. As soon as m equals n, we take the coefficients here. So our horizontal asymptote is y equals, we can either put 2 over 1 or just 2. And our vertical asymptote is x plus 1 equals 0. We bring over the 1. It occurs at x equals negative 1. Now for D, we have x to the 1 over x to the 1. So we simply take the leading coefficients for our horizontal asymptote. So we have y equals 3. You can do 3 over 1. It's tedious. Y equals 3. Now, vertical asymptote, we take the denominator. Vertical asymptotes occur every time the denominator equals 0. So we just isolate for x, and we get x equals negative 2. Okay, so let's talk about steps to test end behaviors near vertical asymptote. So what does this even mean? Okay, so when we approach a vertical asymptote, when we're dealing with a rational function, what's going to happen is, let's say we have a vertical asymptote here. One of two things is going to happen. We're either going to approach that asymptote and approach infinity, or we're going to, let me delete this because these don't exist at the same time. Okay, or we're going to approach this asymptote and approach negative infinity. Okay, and then that's talking about approaching this asymptote from the left. Now, from the right-hand side, we would do the same thing. Are we going to approach infinity and it look like this, or opposite, are we going to approach negative infinity? Okay, so this is the way we need to test every single time we have a rational function. We need to test whether we're approaching that vertical asymptote from the left or the right, or sorry, the left and the right, approaching infinity or negative infinity. So what we're going to do is we're going to list each factor of the simplified equation going down the first column, okay? So x minus a, x minus b, whatever it is. This is just an example. Then we're going to list each 0. So there's two things here. We're going to list each 0 and each asymptote in numerical order. Okay, we saw that when we were graphing polynomials, where we want to do it kind of like a number line. So in numerical order. But what we're going to do is we're going to list each asymptote twice. So say k is an asymptote. We're going to list k from the left and k from the right. And this superscript negative and this superscript positive is how we're going to depict from the left and from the right. That's what those mean. Okay? Then I just put m as like x-intercept. Then n from the left and n from the right. We can clearly see that n would be a vertical asymptote as well. Okay? So, note each asymptote is listed twice. Okay, one from the left, one from the right. We have that. And then what we're going to do is analyze the positive and negative signs and determine if the graph approaches each asymptote going to negative infinity or this should be positive infinity. Okay, and then all we do is we go to the graph and we draw little mini arrows. So the arrow could look like this, or down and down. Okay, and we just draw arrows. We don't draw the entire thing because we don't know where we're going to end up for the horizontal asymptote, but we just sketch it in first. Okay, now let's talk about end behaviors near horizontal asymptotes. So essentially what we're going to be looking at for this one is we are going to take a look at horizontal asymptote, wherever it is. I'm going to do this one at 0. That's fine. Okay. And we need to know whether we approach the horizontal asymptote to negative infinity above. So like if the arrow is going to go here, or below. And then if we're going to approach to positive infinity, either above or below. Okay, so how we're going to do that, because we're approaching positive infinity or negative infinity, what we're actually going to do is we're going to test an extreme value. So the extreme values for us, like for the scope of like what we need, we'll just do 100 or negative 100. Okay, and those 100 and negative 100 will actually represent like a really big number, aka positive infinity, or a really small number, negative infinity. Okay. And then what we're going to do is we're going to take we're going to sub in those like x equals negative 100 and x equals 100 and evaluate. We're going to get some number. Then what we have to do is we have to take that number and we have to compare it to the actual horizontal asymptote. So will that number be above or will that number be below the horizontal asymptote? And then that's where we're going to be drawing our arrows. Okay. So example 2, determine how the graph of f at x equals 3x minus 5 over x plus 2 approaches its vertical and horizontal asymptotes. So first of all, let's actually state the vertical and horizontal asymptotes. Okay, horizontal asymptote, we have an x over an x, so our horizontal asymptote is at y equals 3. Our vertical asymptotes are going to be whenever the denominator equals 0, so we get x equals negative 2. Okay, the other thing that we need to consider is the x-intercept, because remember, for the vertical asymptote chart, we need to determine the x-intercept. So let's sub in y equals 0. So 0 equals 3x minus 5 over x plus 2. If we were to bracket the x plus 2 and cross multiply to 0, it's just going to go away. So essentially, the x-intercepts are always going to be what the numerator, when the numerator equals 0. So let's bring this over. We get 5 equals 3x. Okay, and then x equals 5 over 3. Okay, so for the VA chart, and we can label that vertical asymptote chart, we are going to put down the side our two factors. We have 3x minus 5 in the numerator, and then we have x plus 2 in the denominator, and then we're going to know the overall sign. Okay, you can put f at x. F at x meaning like the entire function. Okay, numerically, negative 2 comes first. So we're going to assess negative 2 from the left side. We're going to then assess negative 2 from the right side. And then we're going to assess the x-intercept. Watch, you'll see the x-intercept, it's easy. Okay, so just like what we did in polynomials, essentially, what is a number on the left-hand side of negative 2? Okay, but you have to think 0, negative 2. You have to think of a number between basically negative 2 and 3, but just on the other side of negative 2, I'm going to use like kind of like negative 2.1, right? So if we have negative 2.1 and we subbed it into the first bracket, this is actually a little bit harder because it's it has like the coefficient of 3. But we're going to have a negative number, right? Negative 2.1 times anything, times a positive number is going to be negative number minus 5. It's going to be more negative. This is where it gets a little like you have to pay attention. Negative 2.1 plus 2, we're still going to be in the negative. So overall, this graph is going to approach the vertical asymptote to positive infinity. Okay, on the left-hand side. Now on the right-hand side, what's a number to the right of negative 2? Maybe negative 1.9 for an example. Okay, negative number times 3 is going to be a negative number, minus 5 is a negative number. Negative 1.9 plus 2 is going to be our positive number. So this graph is going to approach negative 2 from the positive side, going to negative infinity. okay? And we always put the x-intercepts in here. However, okay, when we sub in 5/3 to this, we get a 0. So 0 times anything is just going to be 0. So that's fine. Okay, so loosely, if I were to graph this and just graph the vertical asymptote at -2, the horizontal asymptote at 3, and I know that the question doesn't ask us to do this, that's okay, and the x-intercept at 5/3, which is approximately here. Okay, this is how we read this. So this means f at x, the function, approaches, that would be an arrow, -2 from the left, and it approaches going toward positive infinity. So let's do this. So f at x equals -2 from the left, approaches positive infinity. So locate your -2, your vertical asymptote, go to the left, and we're gonna just draw the head of an arrow there. Okay, and then this one means when f at x equals -2 from the right, we're going to approach negative infinity, right? Because negative. So locate your -2, and then we're going to draw a negative infinity, right? Because this goes towards negative infinity on the right-hand side of that. Okay, now let's do the horizontal asymptote chart. Okay, so a little bit different here. The horizontal asymptote is y equals 3. So there's only 2 calculations that we need to do. We need to look at when x approaches negative infinity and when x approaches positive infinity. So we can go ahead and sub in like 3 times -100 minus 5 over -100 plus 2. When you throw that into your calculator, you're going to get 3.11. And you're going to do the same thing, but with the positive 100. And we're going to get 2.89. So as you can see, our horizontal asymptote is 3, and we're getting 3.11 and 2.89, right? We're getting numbers very, very, very close to 3. So we have to assess 3.11, is that above 3 or below 3, right? Because we're thinking like 3.11 is going to be above 3. So as x approaches negative infinity, which is our x's approach negative infinity, oh, maybe I'll do this in purple, we are going to approach above that asymptote. And if we take a look at 2.89, the actual number, and we compare it to 3, that is definitely below that asymptote. Okay, so as we approach positive infinity, which is way over here, locate the asymptote, and we're going to approach from below. So if we were to connect these arrows, this is what our graph is going to look like. Example 3, determine how the graph f at x equals negative x plus 2 over 2x plus 6 approaches its vertical and horizontal asymptotes. Okay, so I'm going to, first off for the x-intercept, here's the thing, we want to do y equals 0 or f at x equals 0. So we're going to go 0 equals negative, okay, x plus 2, and essentially this is like 2x plus 6. I'm going to bracket both of these just so that we can group those binomials. Now, when we cross multiply, we get 0 equals just the numerator. Okay, we've seen that before. Divide both sides by -1. We get 0 equals x plus 2. Okay, bring over that positive 2, it becomes -2. X equals -2. Okay, vertical asymptote. It's going to be the denominator. So 2x plus 6, when does that equal 0? Okay, 2x equals -6. Divide both sides by 2, we get x equals -3. Okay, and taking a look at this, let's talk about the horizontal asymptote. Okay, we have the degree in the numerator is equal to the degree in the denominator. We've been calling them n and k because it's x to the 1 over an x to the 1 term. So what we want to do is just take the coefficients. So I get y equals, I get -1 on the top, right? Because this negative sign, simplifying it, goes to the top. And then the coefficient of the denominator, like the x in the denominator, is 2. Okay, so there is our horizontal asymptote. Okay, let's do the vertical asymptote chart first. So we want to write our factors down the left. Okay, we have -1. Okay, treat this negative sign here just as a -1. And guess what? It's always going to be negative every single time because there's no x in it, right? So we're not actually subbing in a value, but we have to take into account that there's like quote unquote like that reflection. If there is, like if that's what it like cancels out to, right? But that negative sign. Okay, the numerator is x plus 2 and the denominator is 2x plus 6. Okay, so we want to include our vertical asymptotes. We want to include -3 from the left, -3 from the right, and then we want to include our x-intercept, which is -2. Okay, and these are numerically in order. So when we sub in a number on the left side of -3, it'd be like -3.1. Okay, subbing it into x plus 2, we get a negative. Subbing it into this, we'd get -6.2 plus 6, so we'd get a negative. So that's going to yield a negative. Now, -3 from the positive side, let's go -2.9. Okay, so -2.9 plus 2 is still negative. And then this is going to be a positive, so that's going to yield a positive. I'm going to double check that. Okay, and then let's sub in -2. Okay, -2 plus 2, obviously that's 0. We don't have to do these two. That just goes down as obviously the x-intercept. Okay, so on the left-hand side of -3, we're approaching negative infinity. And on the right-hand side of -3, we're approaching positive infinity. Okay, now horizontal asymptote chart. Let's do that in like baby blue. Horizontal asymptote chart. We are going to take a look at when x approaches negative infinity and when x approaches infinity. Okay, so we're going to sub in -100. So we have negative of -100 plus 2 over 2 -100 plus 6. And we get -0.505. Okay, and then we're going to sub in positive infinity, but we're going to sub in 100 as just like a positive infinity, as in like a really big number. Okay, and we get -4.95. So here's the thing. We have to compare these two numbers to the horizontal asymptote. So compare, I'll write a note, compare to y equals, well, it's like -0.5, right? So -0.5. So -0.505 is actually below because it's more negative, right? It's a bigger negative number, so it's actually below this asymptote, and -0.495 is actually above because it's still a negative number, but it's a smaller negative number. Example 4, fill in the chart for each of the functions below. So let's start with f at x equals 2 over x minus 3. Okay, intercepts. In order to find the x-intercept, we have to sub in 0 for y. Well, here's the thing. If we do 0 equals 2 over x minus 3, and we cross multiply this, we get 0 equals 2. Well, we know that's never going to happen. So there's no x-intercept. And I do want to point out, it's because this is a reciprocal linear function, right? It's a constant over a linear equation. So the horizontal asymptote's actually y equals 0. Okay, so y equals 0 is our horizontal asymptote. So it's right on the x-axis. And that's why there's no x-intercept. Okay, y-intercept, we're going to sub in a 0 right here, and we get negative 2 over 3. Okay, so we can go ahead and plot that. Okay, so the domain is XER such that x does not equal, let's do the asymptotes first. Okay, the vertical asymptote is going to be when x minus 3 equals 0 because that's the denominator, so x equals 3. So going back to the domain, x cannot equal 3. Okay, vertical asymptote at 3. And we'll go ahead and draw that. Okay, so as a quick sketch, we know that this is not reciprocal, so, or sorry, this is not reflected, so it's just going to be in these two quadrants, okay, or these two areas. Now, positive intervals, positive is above the x-axis, so this is 3 to infinity. Negative intervals is going to be this part of the graph, which is negative infinity to 3. And this is decreasing on XER. Okay, except for obviously where the asymptote is, because our graph is undefined at that asymptote. Okay, and there's no increasing. Okay, f at x equals x minus 2 over 3x plus 4. So let's do the x-intercept, so sub in y equals 0. Okay, when we cross multiply the denominator, we just get, the x-intercept's just when the numerator equals 0. So we get x equals 2. Okay, for the y-intercept, we sub in a 0 here and a 0 here. So we get negative 2 over 4, which is negative 1 over 2. Okay, let's do the asymptotes first. Vertical asymptote is when the denominator equals 0. Okay, so bring over the 4, we get 3x equals negative 4, and divide out by 3. So the vertical asymptote is x equals negative 4 over 3. And the horizontal asymptote is the coefficients here. So y equals 1/3. Okay, let me graph this. So x-intercept is 2, y-intercept is negative 1/2. Vertical asymptote is negative, it's like 1 point, like negative 1.3. Okay, negative 4 over 3. I should label them. Y equals 1/3, so horizontal asymptote is just above. Okay, so that means for the domain, XER such that x does not equal the vertical asymptote, which is negative 4 over 3. So let's go ahead and graph this. We can see that like we have an x and a y intercept in this part of the graph. So we will graph it here and here. Okay, so the positive intervals are going to be negative infinity to negative 4 over 3. Okay, and then again negative 4 over 3 to this x-intercept, which is 2. Negative intervals are going to be Sorry, yeah, that's positive. Oh no, that's negative. My mistake. We're going to go from 2 to infinity again. And then the negative interval is here. So it's going to be negative 4 over 3 to 2, which is the x-intercept. Okay, this is increasing on xer such that x does not equal negative 4 over 3. And there is no interval of decrease. All right, last one. So I'm going to just erase this on the side. So we have f at x equals x minus 2 over 2x minus 6. Okay, asymptotes. Y asymptote or x-intercept. Sorry, intercept. So x-intercept sub in 0 for y. So we get 0 equals x minus 2. So we get x equals 2. Okay, y, we sub in a 0 and a 0. 2 over 6 is just negative 2 over negative 6 is just 1/3. Okay, asymptotes. The vertical asymptote is when the denominator equals 0. So it's when 2x equals 6, I get 3 for the vertical asymptote. And the horizontal asymptote, because there's an x and an x, we're just taking the coefficients. So y equals 1/2. Okay, so the domain is every number except for the vertical asymptote, which is 3. So let's go ahead and plot 2, 1/3. Vertical asymptote is at 3. Okay, horizontal asymptote is at 1/2. See how I kind of, okay, wait 1 second. Intercept is 1/3, so yeah, it's below. Okay, that's fine. Horizontal asymptote, yeah, y equals 1/2, x equals 3. Okay, so this is going to be here, and then this is going to be here. So positive intervals are going to be, remember, this is the 3, so 3 to infinity. Hold on, that's going to be the second one. The first one is going to be negative infinity to this x-intercept, which is 2. Negative infinity to 2. Negative intervals are going to be 2 to 3. Okay, and this is decreasing on xer. Well, sorry, on the domain. So we'll do intervals of increase are going to be none. Intervals of decrease are going to be on the entire domain such that x does not equal 3. 3 being the asymptote. Example 5, the function p at t equals 30, 7t plus 9 over 3t plus 2 models the population in thousands of a town t years since 1990. Okay, so t years since 1990. Describe the population of the town over the next 20 years. Okay, so essentially what we're going to be looking at is t equals 0, so this is time, and then this is 0, which is 1990, and we want to look at the population to year 20, which is 2010, as an example, okay? And this is population. So if we think about the x-intercept, we're thinking about when y equals 0. So let's just take a look at the numerator when that equals 0. So dividing by 30 just gives us 7t plus 9 equals 0. Okay, we get 7t equals negative 9 over 7 over 7. T equals negative 9 over 7. So if we're looking for the t-intercept, we'd actually have to go into like the quadrants that don't actually exist in regards to population and time. And like this would be negative 9 over 7. It'd be some intercept over here. Okay, so that's fine. So let's do the y-intercept now. So let's sub in 0 for t. So population at 0 equals 30. 7 times 0 plus 9 over 3, 0 plus 2. So that goes away, that goes away. We have 30 times 9 over 2. I get 135. Okay, so our population, our y-intercept is 135. Okay. Now, our vertical asymptote is when the denominator equals 0. Okay, bring that over. 3t equals -2. T equals -2 over 3. So we're going to have some vertical asymptote here. Okay, where we approach, like, say, to infinity. And now let's do the horizontal asymptote. So if you think about expanding the numerator, we would get 30 times 7, so 210t plus 9 over 3t plus 2. We're just going to take the coefficients here. So our horizontal asymptote would be 210 over 3, which is 70. Okay, so we're going to have a horizontal asymptote at 70. So this part of the graph doesn't actually exist, like in real life, because we're talking about time and population, but I just wanted to draw it just to have a complete sketch. So how we can describe this is, like, in 1990, our population starts at 135, my mistake. Okay, and then it decreases, and it decreases for the next 20 years, because we only care about the 20 years, approaching, okay, and we're going to approach, obviously, the horizontal asymptote, so approaching 70, okay, and this is obviously 70,000, right, because the scale is in thousands, and this is 135,000.